Hi guys, so in today's video we're going to start talking about the derivative. The derivative of a function allows the gradient or instantaneous rate of change of that function to be determined at any point. For this reason, it is sometimes referred to as the gradient function. The derivative or gradient function is itself a function. And finally, as we'll see shortly, the gradient function or derivative is able to provide the exact gradient of a function at a point, not just an approximation. In order to understand where the derivative comes from, we'll need to take a step back and look at some of the maths. In order to understand where the derivative comes from, we're going to need to take a step back and look at some of the maths that we've been exploring over the last couple of weeks. So if we have 2 points, x1, y1 and x2, y2 on a function, the average rate of change of that function between those 2 points is simply given by the gradient of the straight line between them. So in this case, delta y divided by delta x, or y2 minus y1 divided by x2 minus x1. But what we are often interested in is the instantaneous rate of change of a function at a point, and that is a little bit more difficult to determine. What we usually do is rely on the fact that the instantaneous rate of change of a function at a point is equal to the gradient of a tangent line drawn at that point. So if we can draw the tangent line, we can take the point of intersection between that line and the curve, which we know exactly, and one other point on that line, and use the same procedure, work out the gradient of that straight line, and that gives us an approximation of the instantaneous rate of change at that point. It's an approximation because we cannot draw the tangent line exactly. It's always going to be slightly subjective. What we really need is a way to work out the exact value of the instantaneous rate of change at that point. Instead of using tangents, we can approximate the instantaneous rate of change at a point on a function by using another nearby point. So we take one point, x, f of x, we take another point that is some small increment of x away, and we'll call this difference h, and so we get another point that's at x plus h, and evaluates as f of x plus h. And what we do is we use exactly the same procedure. We find the gradient between these 2 points as m equals delta y over delta x, which in this case gives us f of x plus h minus f of x divided by the difference in their x values, which is h. Now this is still only an approximation, actually just finding an average rate of change, but between 2 points that are very close together. And so there hasn't been very much time for the function to have changed its gradient significantly. Now, of course, the closer we take those 2 points, the better the approximation will become. And this leads us to our final point. And that's that we can use another bit of maths we've learnt about recently, limits, to take those points closer and closer together. And the answer then will become closer and closer to being the true gradient of the function at that point. And so what we're going to do is we're going to define this answer as our derivative. So our derivative, f dash x, is going to be equal to the limit as the distance between those points vanishes, as h approaches 0, of that gradient that we had before. So f of x plus h minus f of x divided by h. And this is called finding the derivative by first principles. So let's take a look at an example. Let's say we've got the function f of x equals x squared plus 3x. And we now move to a point nearby at x plus h, and that evaluates by replacing every x with x plus h. So we have x plus h squared plus 3 lots of x plus h. Expanding this bracket, we get x squared plus 2xh plus h squared. And the second bracket, we've then got plus 3x plus 3h. We now have everything we need to work out our derivative function. So f dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And that's equal to the limit as h approaches 0 of x squared plus 2xh plus h squared plus 3x plus 3h minus, and we're going to use brackets here because it's important to remember that we're taking away everything. So we're subtracting off x squared plus 3x. And that minus is going to apply to both of those terms. And we'll divide all of that by h. And what's going to happen here is this term and that term are going to cancel. This term and that term are going to cancel. And that's always going to happen. And so what we're left with is the limit as h approaches 0. And we're going to divide our h out now because you'll notice that every term that remains has an h in it. So we're going to get 2x plus h plus 3. And it's pretty easy to see that the limit of this function as h approaches 0 is just going to be 2x plus 3, because that middle term h is just going to disappear. Its value is going to be smaller and smaller and smaller until it's infinitely small and therefore has no effect anymore. Whereas the value of x remains unchanged, and obviously 3 is a constant. What that tells us then is that this function 2x plus 3 is the function that tells us the gradient of our original function x squared plus 3x at any point we care to name. So, for example, we could have f dash at 2. And what we get is 2 times 2 plus 3 equals 7. And so at x equals 2, if we went back to our original function, what we would find is that the gradient at that point is equal to 7. And we can substitute any x value we like. And this function, 2x plus 3, will tell us what the gradient is at that point of the function x squared plus 3x. Before we end, we'll just take a quick moment to talk about notation for functions and their derivatives. It's important to realize that the history of differentiation actually came about through several different mathematicians who independently came up with many of the ideas of differential calculus. And each of them created their own notation. And many of them have survived to this day in mathematics, to the point where there are concurrently about 4 different ways that you can represent differentiation, 3 of which are very commonly used. So we've already seen that if we have a function written as f of x, that we can write its derivative as f dash of x. In the same way, if we have the function written as y equals, then we can write y dash, or y prime. That symbol is known as a prime symbol. This notation comes to us from a mathematician named Lagrange. But there were others. So we've also got that if we have a function f of x, we can write its derivative as d dx of f of x, which is not a very neat notation. It's more commonly used when we have y, because then we can write dy dx. This notation comes to us from a mathematician named Leibniz. Newton also came up with his own notation, and that's if we've got some function y, then the derivative can be written as y dot. So that was Newton. There's a note on this one now. This one is only usually used to denote differentiation with respect to time. So if y is a function of time, then y dot is its derivative. Finally, if we have our function f of x or y, we can represent differentiation using capital D. This notation is very rarely encountered and comes to us thanks to a very famous mathematician known as Euler. Most of the time, you'll be using the first two sets, the Lagrangian and Leibniz notations, using primes and dy dx. Those will be the two that you'll see in your textbook most commonly and that we will use when working these problems. The Newtonian notation, the dot notation, is actually most commonly encountered in physics, because in physics many of your formulae are for systems that evolve over time, and so you're often finding derivatives with respect to time.